We're gonna cover fracture mechanics. Fracture mechanics is um, a way of predicting what this the what the structure can survive if a flaw was to be present. So linear elastic fracture mechanics is applied to a lot of different materials where crack tip plasticity is small compared to the crack length. So the formula to predict fracture depends on the fracture toughness, stress level, geometry, and crack length. So material fracture toughness can be defined as the ability to carry loads, and it can be described in terms of the stress intensity factor. That can be measured through a test, and it's a material property. Crack size is a fracture initiates from discontinuities that can vary from extremely small cracks to much larger welds or fatigue cracks. And then the stress level, what stress level the parts has. These three things together combined with the geometry of the part tells us what the stress intensity factor is, which is a way of measuring whether the material is capable of fracturing. The formula for stress intensity factor looks like the one shown here. I have a whole lecture on YouTube that covers fracture mechanics, so this is a very top level view. The stress intensity factor is for cracks in the infinite body, the one that I'm showing here. However, the finite size and geometry of the component are usually covered in Y. So if Y was not there, there's usually a crack in an infinite plate or approximating that way. And this stress intensity factor tells us how intense the stress field is. If K1 is greater than the fracture toughness of the material, then crack propagates. Here is the crack length. Pi is 3.14159. Stress, here is the stress level you apply. K1 is the material property. So this should be very easy to calculate. So for example, I know the crack length for infinite plates. I plug in half. Usually the formula here is going to be, if this is 2A, this formula becomes A there. Yeah, so it's pretty straightforward. Hold on. Okay, we'll continue here. Okay, I'll continue, but we can now predict the fracture toughness. We'll continue. Fracture toughness is a measure of the ability of the material to resist the growth of a pre-existing crack or flaw. And this fracture toughness of the material is characterized by the energy per unit area, which is required to create a new crack surface. This is also known as critical stress intensity factor. These are the various tests that can be used to measure the fracture toughness. You have the CT test, the compact tension test is what this is. This is the single end notch beam test. And then you have other tests like the taper, double cantilever beam, and other things like that. So fracture toughness testing can be performed to measure K1C. So a steel ship deck is 30 millimeter thick. So we know it's 30 millimeter thick, is 12 meters wide. So that's this right here. 20 meters long, which is this one here, and has a fracture toughness of 28.3 megapascals square root of M. So that's a material property, was measured in advance. If you have a crack length that's 65 millimeters, calculate the nominal tensile stress that will cause catastrophic failure. So we want to know what tensile stress can be applied to this system before failure occurs. We'll then use this formula here. We'll use K1 equals Y times sigma, the stress, squared root of pi A. Because these plate dimensions are so big, this is in the meters and this crack is in millimeters. That means that this is almost like an infinite plate. And there's a bunch of formulas, like a list of formulas, closed form solutions that you can use to actually solve a lot of these problems. In this case, for a flaw in a large infinite plate, you have that y equals 1. So that's 1. And that can be found in a handbook of formulas, for example. Stress here is known. Actually, we don't know stress. We want to know what it's asking what the tensile stress is. We have pi there, and then we have the crack length, which is 65 millimeters. But the A that goes here is half that crack length. And so it's 32.5 times 10 to the minus 3. So K1 is equal to Kc because that's when fracture occurs. So that's 28.3. I can solve for stress now, and the stress is 88.6 megapascals. That's when failure occurs. Uniaxial stress at which yielding begins is sigma yield equals 240 megapascals. You can check that yourself. And you will see that in reality, fracture will occur before anything else. And fracture will be occurring at 88.6, and especially because this is lower than the yield of the material. Example number 2, I have a plate now, but there's an edge crack here. The edge crack is 2.7 millimeters. The width is 1.4 meters, and this length is 2.8 meters. And I apply a load here. You can see here that stress, you can write the factor of safety. So factor of safety is stress at the yield divided by the stress applied. The stress applied is this load applied, P, divided by the cross-sectional area, which is B, the thickness, times this B here, this length here. So that's sigma yield. I can solve for the thickness. I get factor of safety times the load divided by the height B times the yield stress. The problem is telling us that there's 2 titanium alloys that need to be considered, alloy A and then alloy B. And it's telling us, hey, which of these 2 alloys gives me the lowest weight solution? So first I'm trying to figure out what design thicknesses I need based on yield alone. And so I do it for alloy A and alloy B using the same formula I derived here. The factor of safety is given as 1.3. The load is provided, I believe the load is provided 4 meganewtons there, which is this number right there. B is known, which is the height of this structure. That's 1.4, which is 1,400 millimeters. And then sigma yield is provided to us as 910. We know that because it's provided to us. Yeah, so that's for alloy. Alloy is 910, and for alloy B is 1035. So let's do alloy A. When I plug everything in, I get that the stress is 700 megapascal. For alloy, and the thickness requires 4.08 millimeters. For alloy B is 3.59 millimeters. You can also calculate the stress if you wanted to. Now, if I want to design to fracture, so this formula here looks very complicated, but that formula comes from a handbook, and that handbook provides the formula for a plate with an edge crack. So you can plug, all these numbers, BA, all these numbers are known because the geometry of the problem is given, the crack length is given. Y, after you do all the calculations, 1.12225, that's what goes in there. K1 then becomes, when you plug all that in, you get 0.103 sigma. You can then solve for Kc, and when you solve for Kc, which is when crack propagates, you solve for sigma, and then you get this equation here at the bottom. For alloy A and alloy B, K, stress is equal to, they told us what the KC is for that alloy A, it was 115, and for alloy B is 55. So I can plug that in. KC is 115, I get 885. That's the stress level at which cracking will occur. The thickness then becomes a load applied, which is 4 meganewtons, divided by the height, which is 1400, times sigma, which comes from this equation, and the thickness becomes 3.34 millimeters. For alloy B, I can repeat the process, and when I do that, the thickness is 6.98 millimeters. And so the lightest weight solution then for this design is comparing all the different numbers we saw, and I'll let you decide. I'll let you decide which one you think is the best solution for the problem. But there's one for yield and one for fracture. You can also apply the principle of superposition. So if I know the solutions for an applied load with an edge crack, but I also know the solution for a moment applied separately, with the edge crack, I can add both of those conditions linearly, as long as I'm not violating the principles of linear elastic fracture mechanics, which state that at the crack tip, the plastic zone should be a lot smaller than the crack length. Here's another example. So here what you see is an example where I have a pressure applied inside a crack. There are solutions for a surface crack with a far field stress. So if I want to study that, I can study this case, and there's a solution for this problem too, where you have a far field stress, but with a pressure applied in compression. It turns out if I subtract these two, I get this problem here because the pressure cancels out, and then you only get a pressure inside the surface. That solution exists. So you can then analyze K for the crack with internal pressure, K1, and you can look at the similar circular crack. I'll let you work through this. It's very straightforward. But the bottom line is you can use superposition for this problem. And that concludes this lecture.